Hi, today we're going to be taking a look at how different gases deviate from ideal behavior and what causes them to behave differently from each other. So the first one that we are going to talk about is hydrogen. Hydrogen has a small size. So basically, first, let's take a look at the compressibility factor, which is a ratio of pressure and volume of that gas divided by the universal gas constant, and it's the temperature of the gas. The ratio of that, if the ratio of that is 1, meaning that pressure and volume, the product of that and the product of the gas constant and temperature is the same, meaning that they're going to get crossed out like this. If those two are the same, and we get a value of 1. So if that is the case, this would mean that the gas that we're going to talk about is ideal gas. So yeah, but if the gas shows deviation from this behavior, we say that that specific gas is a real gas or it's a non-ideal gas. So first, we have to know that this is a positive deviation, meaning that it's going only up, meaning it's only like going towards above 1. And this is a negative deviation, meaning it's coming below 1. Okay, so it's going down, and that's known as a negative deviation. And what influences these deviations? And there are two factors that influence such things. Positive and negative deviations depend upon intermolecular forces. So if, let's suppose, the molecules that we are talking about actually are nonpolar, so the forces that we're going to talk about in their case are going to be London dispersion forces. Now we know that London dispersion forces depend upon the size, meaning the greater the size, the greater the London dispersion forces are going to be, and meaning that the attractive forces are going to be more. So if a molecule's size is more, this means that the London dispersion forces in the molecule are going to be more, and they're going to be more attracted towards each other. Okay, and the second one is molecular volume. How much molecular volume is there? But molecular volume is also a factor which basically determines whether the deviation is going to be positive or it's going to be negative. So there's going to be basically the molecular volume has to be considered when you are talking about real gases, because real gases, when they are compressed and there's a lot of pressure applied on them, they're going to not their the volume of the single gas molecule does not become negligible anymore. It's not negligible anymore, it is something. So that's why there's going to be repulsion when they come close to each other, and that's why it's going to show deviation. So let's first look at hydrogen. Now hydrogen shows only positive deviation. Why is that? This is because hydrogen has a small size. So a smaller size means lesser London dispersion forces, which means lesser attractive forces. And hydrogen is the smallest, which means that it's going to have the least London dispersion forces, and as a result, attractive forces between hydrogen molecules are not going to really exist in a gas, because they're very far apart from each other as well. But as you apply, now there's going to be no attractive forces. So when you apply pressure on hydrogen, the hydrogen molecules are not going to come close to each other. But due to hydrogen having electrons in its valence shell, and the different hydrogens are going to have different valence electrons, and those valence electrons are going to repel each other due to there being a molecular volume of hydrogen. So this is why we say that when we increase the pressure in the start, you can see that hydrogen shows ideal behavior. It has a value of Z equals to 1. However, as you increase the pressure, hydrogen's behavior changes. It's not ideal anymore. It shows a positive deviation, meaning it becomes less compressible than usual. there's going to be repulsion between the hydrogen molecules being forced together. So as a result of that repulsion, the hydrogen molecules are going to push back on each other, and they're going to apply forces on the container walls, and they're going to expand. The molecules are going to expand. They're going to go far apart from each other due to the repulsion, and as a result, hydrogen shows positive deviation. This thing, you can see PV equals to 1. 1 means that the volume, okay, this is basically that these two values are the same. But if you see, like when you see that the compressibility factor is increasing, this basically means that pressure is increasing. Of course, pressure is increasing. Temperature is taken constant. This is actually, this whole graph is for a temperature of 313 Kelvin. So that's something to keep in mind. So the only thing that's changing really is the volume. And this compressibility factor is also changing because of a change in volume. So you can see as we are increasing the pressure, the volume is going to increase for hydrogen because the compressibility factor is greater than 1 for hydrogen. So this is why we say that it has, it only shows positive deviation. Whereas let's look at carbon dioxide. Now, carbon dioxide has a relatively large size, due to which it's going to have greater attractive forces, meaning London dispersion forces. So when we apply greater pressure, so okay, the pressure is not so great that the molecules are going to come close to each other, but still the molecules are going to come within each other's fields. And when they come within each other's fields, they're going to attract each other. And as a result, you can see that we know that temperature is kept constant here. Pressure is increasing, of course, but in this case, volume is going to decrease. Why? Because the two molecules of carbon dioxide, let's suppose, they're going to attract each other because of, higher London dispersion forces, being highly polarizable. Carbon dioxide is highly polarizable because of its large size. So London dispersion forces are going to be greater, and as a result, what's going to happen is that the carbon dioxide molecules are going to attract each other, and there's going to be a greater volume decrease than usual, and that's why there's going to be a drop here. But as the pressure increases, the carbon dioxide molecules are going to come closer to each other, and since they have a molecular volume, there's going to be at last some kind of repulsion between those carbon dioxide molecules, because you can't force them into each other, you can't fuse them together, you can't fuse the two molecules. So because there is going to be some kind of size for them, this is a real gas we are talking about, so it's going to show positive deviation. Why? Because there's going to be repulsion between the electrons of the valence electrons. So there's going to be repulsion, and they're not going to want to be close to each other anymore, and they're going to show positive deviation then. So first negative because of attractive forces, then positive. So this is all because of the size difference. Hydrogen has a small size while carbon dioxide has a larger size. So hydrogen has no, you could say, London dispersion forces, while this does have. So at first there's going to be a decrease in volume because of attraction. Then because of the further pressure being applied, there's going to be repulsion. That's why there's going to be negative deviation than positive. For nitrogen, since its size is smaller than carbon dioxide, hopefully, so that's why there's going to be a slight negative deviation, but it's going to then show positive deviation because of the fact that its size is slightly smaller than carbon dioxide. So there's not going to be as much attraction between the nitrogen molecules, but it still does have some kind of attraction. So there's going to be some negative deviation. Methane has a bigger size than nitrogen or not, but it's still going to have some kind of London dispersion forces, and it's going to have this. So this is why, this is the fundamental concept. There are, of course, more deeper things regarding the different behavior, but this is only why this is just a reason that is presented to you on why there's going to be deviation, positive and negative deviation from ideal behavior. Yeah, I hope you guys understood this lesson, and yeah, I'll see you in the next one.